Welcome to section 3.5, circular functions. At the end of this lecture, you should be able to answer these three questions. What is a circular function? Why is it important? And how will we distinguish between trigonometric functions measured in degrees and circular functions measured in radians? Well, first of all, what is a circular function?
Circular functions are the same as our trigonometric functions, except they're using radians instead of degrees to calculate our values. If we use a unit circle and pick a point on the edge of our circle, u comma v, u would be the adjacent side of our reference triangle, v would be the opposite side of our reference triangle, and our hypotenuse would be 1, which means that our u coordinate is actually the cosine of x, the adjacent side over 1. And our v coordinate is the sine of x, or the opposite side over 1.
Our textbook is unique in that it gives us a hint as to whether we're working in radians or degrees by using different variables to represent the two different scenarios. For circular functions or radians, our textbook will use the variable x to denote the angle, whereas for trigonometric functions, those we're evaluating with degrees, our textbook will use theta to denote the angle. Let's look at an example in radian mode. We're going to plot y equals 4 cosine of 5x. We're going to find the period graphically and algebraically and see if they match. So let's start by plotting the graph of y equals 4 cosine 5x. Pull out our calculators. Now I've already input the equation here for cosine 5x, and to set the appropriate window I'm going to do a zoom trig, or zoom option 7. And we'll check our window here. And we'll see that instead of going from negative 360 degrees to positive 360 degrees, we're going from approximately negative 2 pi to positive 2 pi, or 2 full periods of the sine or cosine graph. If I look at my graph, I can see several periods, but that's because we have a horizontal dilation. To find the period, we're going to measure the distance between two maximums because that represents one full cycle. To find the location of my first maximum, I will go into second trace or calc, and look how conveniently we have option 4 here, maximum. So I'll choose option 4, and it'll ask me where do I want to set my left bound. I'm going to look at this maximum here, or the distance between these two maximums here. So I'll set my left bound to the left of the first maximum, my right bound on the other side of that maximum, and guess. And I'm going to take that value where y equals 4 of x equals 1.2566. Now, I'm going to take that value that's stored as x. If I type x right now, you'll see that that's the value that's being stored in the variable. I'm going to take that and store it in another variable that I'll call a, and go back to my graph now that I've saved that information, and I'm going to find where that second maximum is, to the right of my first maximum. So I go back to second trace, ask for the maximum, option 4, and I move across to my next maximum, or just to the left of it. And then it asks me for the right bound, so I move to the other side again and hit enter, ask again, and I get a new maximum at 2.5133. I'm going to go back to my home screen, and if I ask for x again, that new value is there. I'm going to store that in B. And to find my period, I'm going to subtract A from B. So alpha B minus alpha A. And we get a value of 1.2566377. So we've determined that we have a period numerically of 1.2566. To find the period algebraically, we remember that our period is 360 over B, except that's in degrees. So we need to adjust for radian mode and change that 360 to the period in radians, which is 2 pi. In this case, our B value is 5, so our period should be 2 pi over 5. If I want to check that on my calculator, I'll take 2 pi and divide by 5, and I end up with 1.256637. Now let's go quickly through an example of analyzing a graph and coming up with its equation, except this time we're going to do it in radian mode. So here's my graph, and I want to determine the sinusoidal axis. To find the sinusoidal axis, we find the midway point between the upper bound here at 5 and the lower bound here at 1, which is 3. So my sinusoidal axis is y equals 3. And that 3 is also the c value in my general sinusoidal equation. Let's continue. Now we want to determine the amplitude. Well, we know that my sinusoidal axis is here at 3, and our amplitude is the distance to the upper bound or the lower bound. And we can see that from 3 to 5 is 2. So my amplitude is 2, which is my A value in my general sinusoidal equation. To determine the period, we simply look at the distance between one maximum and the next. We go from 1 to 11, so the period is 10. To determine the horizontal dilation, we have to take into account that the original period of a circular trig function, like sine or cosine, is 2 pi. To go from 2 pi to a period of 10, I would need to multiply 2 pi by 10 over 2 pi. So this 10 over 2 pi is my horizontal dilation, which if I simplify is 5 over pi. To determine the B value in my general sinusoidal equation, we remember that B is the reciprocal, or 1 over the horizontal dilation. Which means that instead of 5 over pi, B is pi over 5. We could also arrive at B by using our formula which was originally B equals 360 over the period of our new function. But now we change the 360 to 2 pi for radians. So this original formula was for degrees. Our new formula is for radians. To determine the phase displacement for cosine, we remember that our original cosine function starts at a maximum on the y-axis when x equals 0. And we measure the distance from the y-axis to the first maximum, which occurs here at 1. So our phase displacement for this image is 1. Finally, if we want to put them all together, we remember that our A value was 2, our phase displacement was 1, our B value was pi over 5, and our sinusoidal axis occurred at 3. The equation that matches all of those is option C. Here's another example. If we want to find the graph of the tangent of pi over 6x, we see that the only transformation we have is a horizontal dilation. Now, for the sine and cosine, our b value comes from 2 pi over the period. That's because the period of sine and cosine originally is 2 pi. As we've learned, the period of the tangent is not 2 pi. The period of the tangent is 180 degrees or pi. So the tangent b formula would be pi over the period instead of 2 pi over the period. Given that our b value, pi over 6, should be pi over the period. So I need a graph with a period of 6. If I look at each of these options, the only one that has a period of 6 is option C, going from -6 to 0 or 0 to 6.